Hello everyone, I'm Fabrizio and I'm going to present this paper that I wrote together with David Spivak. This is not a new paper, it came out about a year ago, but the reason why I'm presenting it now is because soon we will be releasing 3 more papers. Basically in the last couple of months or so, I realized together with other people that this was just like the tip of the iceberg. There's much more to say on this. So this is one of the reasons, and the other is that not everyone prefers reading papers as a way of learning things. Indeed, many people, me included, feel like they learn way better if they can watch lectures or something similar. So I thought it was nice, it would have been nice to provide people like me with, a more efficient way of learning what this stuff is about. So without further ado, this paper is about Petri nets, and in particular doing colored or guarded Petri nets using category theory. So let's start from the very basics. What is a Petri net? A Petri net is basically something that is made of two different kinds of entities, places that are denoted with circles, and transitions that are denoted with rectangles. And transitions are connected to places via arrows. Now, if a place has an arrow pointing into a transition, we say that this place is an input of this transition, and we can put as many arrows as we want. Instead, if the arrow is pointing out, then we say that this place is an output for this transition. So, like we can have things like this. And Petri nets are basically important in the study of concurrency. They are a very good model to describe in simple terms what happens when you have concurrent systems, like a distributed network of computers, for instance, and resources are shared around this network. So we represent resources as tokens, which are depicted as small black dots inside of places. And basically, we say that transitions move tokens around by firing. Firing is an atomic operation, which means that a transition takes tokens from its input places as prescribed by the arrows and spits out tokens in the output places as prescribed by the arrows. So for instance, in this case, you see that this transition here, let's call this T, cannot fire because T needs 2 tokens from the place on the top, and there is only one. But if we put another token here, then T can fire, and when T fires, these tokens here disappear, and a token appears here. And then this token can be processed by this other transition, let's call it U. When you do, the net becomes empty. And so you can look at the runs of the net, which means all the possible ways of firing transitions. And long time ago, basically in the 90s, people realized that the executions of a Petri net, so all the possible runs of a Petri net, can be described categorically. And the way we do it is actually intuitively simple. We start with this net, for instance, let's call it N. Let's name places and transitions. And now we say that we create a new category, which is a free, symmetric, strict monadal category, call it free of N. And this basically has as generating objects places of N, and as generating morphisms transitions of N. Okay, so for instance, an object in f of N will be something like this. And this represents a marking. This is basically saying that we have 2 tokens in A and 1 token in C. And the morphisms in this case will be generated by identities, symmetries, and this morphism here, and this morphism here. So basically every morphism in the free of n, the free symmetric strict model category, which will represent a way of starting with some tokens and moving them around and getting something else in the end. Importantly, this is not the only way to do this. Basically, there's huge amount of work that has been done on this. I released a paper together with John Baez, Jade Master, and Mike Schulman days ago, in which we give a very systematized view of all the possible ways of doing this. You can use Petri-nets to generate free symmetric strict model categories or commutative strict model categories. You can use pre-nets, you can use other flavors of Petri-nets. And the main tenet of this kind of thing is that you want to produce an adjunction between a category of some flavor of Petri-nets and a category of monoidal categories of some sort. But anyway, this is a story for another day. In here we are focused on guarded nets, also called colored nets. So what is a guarded net? A guarded net is basically a Petri-net where tokens can have properties. So for instance, before we had that our tokens were just like dots that we placed in places. In guarded nets, these are properties. So we can have like a token with the property star, one with the property square, and one with the property circle. And every place can have its tokens with its properties. And now inputs and outputs of transitions are decorated with guards. So what are guards? Guards are just like specifications of which token a given transition can accept. So for instance, if I write this basically means that this transition here will accept only star tokens from the place on the top. So for instance, if I erase the star token, now this transition is not enabled because there is no token with the property star, and square and circle do not work well. If I put a star here, then transition can fire, and when the transition fires, it consumes star, triangle, and spits out, for instance, square. Here. Okay. This is useful because basically gives us finer control on how concurrency works in our system. So in Petri-nets, it's common that you can have a place and you can have multiple transitions going out of that place. And the point is, sometimes you don't want these two transitions to be able to act on everything that ends up in this place. You want to differentiate the behavior. You want to say, if the token in here is of this sort, then you apply this one, otherwise you apply this other one. And this is exactly what guards give you. But an interesting result says that actually, if your guard language is simple enough, then you are able to compile a guarded net back into a Petri-net. So you are able to translate, to get rid of the guard language and get a possibly bigger Petri-net that does exactly the same kind of stuff. This is exactly the thing that we want to explore categorically. And we do this by basically starting with a net and encoding the guard information, the color information, into a functor. So we give this definition here, definition 1. Basically, we say that a Petri-net with an S semantics, where S is a strict model category, is a pair where the first component is a net and the second component is a functor that goes from the free category generated by the net to the semantics. And this is basically, yes, encoding this idea that we are endowing tokens and transitions with properties. And in particular, we consider two kinds of semantics here that are set, star, and span. So sets and partial functions and spans of sets. Basically, what happens is that if we consider, for instance, a net with a semantic in set star, then what we are doing is we are saying for each place of the net, we map each place into a set. Oh, an important thing, remember that we said that this category is called free symmetric strict monodal category. The reason why it says free is because as soon as you say where generating objects and generating morphisms go, you get a functor, a strict monodal functor. So basically to define this functor here, the only thing I have to say is where the objects, generating objects and generating morphisms go. And these are precisely the places and transitions of our Petri net. So this is why I can represent these functors as I'm doing here. So I'm saying I'm sending a generating object corresponding to this place down here to this set, for instance. And I'm sending the generating morphism corresponding to this transition here on the left to this partial function up here. And now you see that each set on top of each place just represents the various properties that a token in that place can have. And the partial function on top of a transition is representing, when the transition uses these tokens, how, the properties of the token that is spit out, which they are, so this one here. So for instance, in this case, you see that this underlying net here seems like enabled. Like if you just look at the net, you may think, okay, I can move this token down here from the left all the way to the right. But actually, when you look at the guards, that's not possible. And that's it because the second transition here on the right only consumes yellow tokens, and the one on the left only produces green tokens. So there's no way to turn this red token here, this token here on the left, into something on the right. So span semantics is basically the same idea, but with side effects. So what are side effects? Well, remember that a span is nothing more than a couple of functions of this kind. And this basically models the idea of having a relation with proof witnesses. So basically, if I have a small s up here and I send it to A here and to B here, then I can say that A and B are related via S. So you see that now in this framework I can also have multiple paths between the same couple of elements, and these paths are decorated with the witness that witnesses the path. So now when I fire a transition, it's not enough to say on which property the token I process has, but I also need to give a proof witness, so I also have to say which path I'm using. Okay, so up to here, this is, I think, all very, very nice, and we can pack this information, as I said, into a strict monodal functor of this sort that goes either to set star or to span, depending on what you like more. Now, category theory gives us a very nice way of modeling this idea that we can internalize this guard semantics. And this is done by using the Grothendieck construction, which is a very famous tool in category theory, which basically turns a functor into a fibration. So what is the idea here? The idea is that we have this net like M sharp, and now we basically want to apply, let's say f of M, this is M sharp, and this is done with set star, yes, okay. And now we want to basically get another category out of this thing, which we write this way, integral of M sharp. And the objects of this category are couples, where the first element is an object of M. So X is an object of M. And small x is an element, of M sharp applied to x. So basically, small x is an element of the set that sits above the place. And what are transitions? The morphisms in this category, where if I have x small x and in here I have y small y, then a morphism f is a morphism that goes from x to y, such that if I apply m sharp to it, and then this will be now a function that goes from the set corresponding to x to the set corresponding to y, and if I evaluate this function on x, I get y. So you see that actually there are as many morphisms there are basically as many morphisms in here as there are paths on top of the morphisms in our underlying category. And indeed, basically we proved that if this functor is strict monoidal, then integral of m sharp is a free symmetric strict monoidal category. This is important because, as we said, we use nets to generate free symmetric strict monoidal categories. And when you have a free symmetric strict monoidal category, you know that there is a Petri net that presents it. And indeed, we can write this thing here in this picture, where you see that basically what the gradient deconstruction does is just like takes this information up here and it balloons every element of these sets into a place and every path into a transition. So basically, this net up here is the internalized version of the guarded net on the left, and it's a fibration on this underlying net we started with. Then the rest of the paper proceeds with some technical stuff. It explains why we can't pull these trick-on relations, for instance, and the reason is that the gradient deconstruction on a functor that goes to rel is not free. And the reason why it's not free is because relations are not proof relevant. They don't keep track of why elements are related. And so when actually you do the gradient deconstruction, you are introducing more equations. And so you lose freeness. And then the rest is basically, again, properties of internalizations. So for instance, basically this whole procedure is functorial. So there's a very easy way of defining what a morphism of these nets are. So remember that our nets have this shape, and I want to say, okay, what is a morphism from here to here? Well, let's see. Basically on the left I have a functor that goes from free of m to whatever our semantics is. And in here I have free of n, and this is n sharp. And a morphism here is nothing more than a functor f that makes this triangle commute. And gradient deconstruction, when our semantics is set star or span, is actually functorial in this respect. So we can lift this morphism of nets to the morphisms of their internalized nets. And then the rest of the paper is spent showing that our construction commutes with colimits and stuff like that. You can glue nets together and blah, blah, blah. But this is not super important. The reason why I really wanted to go into this thing and present this thing is because basically this is a very particular case of a more general theorem that says that the slice category cat over free n is equivalent, seen as a one category, is equivalent to the category of lax functors from free n to span. So what does this mean? It means that an element in cat over free n is just a category C and a functor in here. And an element in here, on the right, is just like a lax functor from free n to span. And the idea is that there is an equivalence which is exactly mediated by the gradient deconstruction. So like if you do like on one side you do the gradient deconstruction of this Lux functor and you get a slice category, and the other way you use another functor, like another procedure. But the point is that we looked into this more in detail. As you can see in this paper, we are only considering strict symmetric monoidal functors to span. But actually, if you take Lux functors, you can do much more than this. And virtually every example we picked gave us an interesting extension of the concept of Petri nets. So we got to the conclusion now that studying extensions of Petri nets is the same thing as classifying these functors here. And indeed, this is a sort of treasure trove because we were able to say already a lot and we are just scratching the surface. So in the next videos, I will present, these new findings that we are releasing now and show you how, you can make use of this equivalence really to say a lot of stuff in the language of Petri nets. Okay, I think that for now, we are done, and thank you everyone for your time. Goodbye.